In this last section of Chapter 19, we're going to talk about more of the sources for magnetic fields and, in fact, talk about how to make an electromagnet. So Ampere's law is really the origin of the equation we used last time for the magnetic field around a wire. And just like Gauss's law is the origin of what we call Coulomb's law, Ampere's law is the origin of the equation we used last time. And so we're going to look a little bit at where that equation has come from. What Ampere's law says, instead of drawing a surface, like Gauss's law says, is we're going to draw just a closed loop. So we're not worried about the area here, we're just worried about the length of the loop. And that loop, we're going to add up the magnetic field. So I'm going to take the magnetic field strength at each point and add it up. And that is equal to this constant mu0, the permittivity free space that we talked about last time, and the current. So it should be no surprise that the strength of the magnetic field is directly proportional to current because the current creates the magnetic field. So what we do is choose an arbitrary path. Again, some shapes are going to be easier to evaluate than others. And then we're going to sum the B and L around the closed path. So what we're going to do is we're going to look at the B parallel to this path, because the magnetic field goes around. Remember, using the right-hand rule, and the total length of the path is the circumference of a circle. So that's where the 2 pi r comes from in the denominator and the equation we used last time. So we're going to look at this example for more how to apply the equation that we used last time, as well as to what would Ampere's law give us for this situation. So again, going dot means we're coming out of the page, and an X means we're going into the page. And so this is basically the wire in your house, where you have one conductor that's conducting electricity one way, another conductor that's conducting electricity in the other direction. So we're going to use our formula that B is equal to mu0 I over 2 pi r. It's more like a 2. And what is r? Well, r is the distance to this point here, if I can draw a straight line. So we're going to say r is equal to the square root of a squared, right, this side of the triangle, plus x squared, this side of the triangle. So then we get, for that particular wire, mu is equal to I over 2 pi times the square root of a squared plus x squared. Now we want to add up the magnetic field at both points. So that's r, but what's the magnetic field doing? Let's see if we can pick a different color. So the magnetic field, remember, is going around. So if we use our right-hand rule and have the thumb pointed out, the magnetic field is wrapping around this way, counterclockwise. So at this point, right, the magnetic field is wrapping around this way, and so the tangent line to that point is going around that way. So that's the B from my top. Then from the bottom, we flip the hand the other way, right? You're going to stick your thumb into the page and then grab your pencil. And so the magnetic field is going to wrap around clockwise. And so the magnetic field at this point is pointing this way. And now we need to look at our angles. So what we're going to be interested in is this angle, which is going to be the same as this angle over here. So yeah, so those are the same angles. So we need to figure out what those angles are. And the total magnetic field, the magnetic field at point B, is equal to the magnetic field to the top plus the magnetic field to the bottom. And so the y components are actually going to subtract and cancel each other out, and the x components are going to be additive. So out here, the net magnetic field we would expect to be pointed straight out. Not really straight, but not drawing it straight, but it should be straight out, is what our net magnetic field should look like. So we're going to separate these into components. That we have B for our top is equal to plus B from the bottom over is equal to B at that point. So B from the top is B top in the x direction I plus B top in the y direction j. And that one is actually, so from the top it's going to be positive, and B bottom xi minus be bottom because it's going down, so it's really a plus a minus j. So what are those values? Well, for the x directions, I'm going to use the cosine of theta because it's adjacent to that side, and we're going to use the sine of theta. Now, am I going to expect you to do a derivation like this? No, but it's good to see that we're going to basically prove that Ampere's law is correct. So we put that in. So the value is mu I over 2 pi times the square root of a squared plus x squared. And now we got to figure out what sine and cosine are. Well, the cosine of theta should be a over the square root of a squared plus x squared, because remember cosine is adjacent. So here's my adjacent side, and over my hypotenuse, adjacent over hypotenuse. And then the sine of theta is x over the square root of a squared plus x squared. Okay, so I'm going to put that in there, and so I'm going to multiply by a times the square root of a squared plus x squared. When I'm multiplying a square root by a square root, I'm basically just going to multiply them together, and that gets rid of the square root. And then I'm going to put a in there for my cosine. So now I've multiplied by the cosine. That gives me I plus, and then mu I over 2 pi a squared plus x squared. But now since I'm multiplying by the sine, it's going to be x. And I do that again for the bottom one, I get exactly the same thing, except this term is negative. So there's 0j, that's what we said we expected. And then we're going to get 2 times mu I times a over 2 pi times a squared plus x squared, right? And that just ends up canceling this 2 out. So that is my formula for the magnetic field at this point. And at this point, the magnetic field is going to be pointed straight out. But is it going to be strong or weak? And does it have anything to do with the distance between the wires and how far I am from the wires? And here's all that math nicely typed up. Basically, we end up with that the top has an A in the numerator for the horizontal component because we're multiplying by the cosine, and we end up with an x for the sine. And then when we add the two vectors together, we have the plus and the minus, so that just ends up being 0. And again, we have the 2 out here, so that 2 cancels, and this ends up being our final formula for the magnetic field around 2 wires, one with current going in and one with a current coming out. So now we want to answer the question, is this a strong magnetic field at this point? So we're not very far away, we're only 5 centimeters away, and the two conductors are 1 centimeter away from each other. So what does that tell us? Is that the magnetic field, when we put those numbers, is 3.84 times 10 to the negative 5th Tesla. We want to compare that to the magnetic field of the Earth, which is it's not very strong, but it's still an order of magnitude stronger than this one. So basically, having these two wires makes a very, very weak magnetic field. And if we want to explore that further, we can look at what happens when these numbers change. So if we get very far away from, so this means far away, so relatively far away, and the wires are relatively close together, what then happens? Well, if we look at that formula, then if x is much, much bigger than a, so a basically disappears from the denominator here, and it's a small number up here, but we're going to look at what happens to the denominator. So as x gets very large, then the b is going to go to 0. So we're going to say that this whole thing is equal to 0. And that's what Ampere's law tells us, is if we have two conductors with current moving in the opposite direction, then we have b parallel, and 2 pi x is our radius for that circumference, is equal to mu times I up plus I down, and this is a net of 0. So that means that the magnetic field is approximately 0 when we have two different currents moving in approximately the same place, but in opposite directions. And here, we don't get b is equal to 0 for all of them, because this assumes that b is constant. And so when we draw a circle around it, certainly it's not going to be constant if we're too close to it, but it's going to be relatively constant as long as we're far enough away. So if we look at what happens is that when we move from just an r to an x squared value, that the magnitude of our field strength drops off much more quickly, like we would expect. And if we look at the distance between the wires, where x is equal to 1, so we're 1 meter away, at very, very close, as long as the wires are very close, then we can approximate the circle, and b is relatively close to 0. However, if we move those wires farther and farther apart so that our circle assumption becomes farther and farther off, then the magnetic field does reach a maximum when a is equal to 1 and x is equal to 1. So that should not be a surprise. We have basically an isosceles triangle here where we have x equals 1 and a equals 1. So that point is when I have the highest magnetic field strength, pointing straight out. And then it starts to drop off as I move the wires farther and farther apart. But in this section, when they are very close together, we get b is approximately equal to 0. There's all those values again. So here's a question for you to think about. This relates to the coaxial cable that you probably have seen if you've ever hooked up a television to an antenna. We use these types of cables. So for Ampere's law, we want to determine the magnetic field outside of a coaxial cable. A coaxial cable means that basically we have an inside conductor and an outside conductor that are basically cylindrical in shape, but they share the same axis. So here we have current coming out of the page. On the outside conductor, we have current going into the page. So in a very small region, we have an equal amount of current going in both directions. So what does Ampere's law say the magnetic field should be? So go think about it for a second. Well, with these two conductors very, very close to each other, since we have I in one direction plus I in the other direction, that sum is going to be 0. So B is approximately 0, which is shown again by Ampere's law. So that's exactly why we use these types of cables to hook your antenna to your television, is we don't want to create a magnetic field because that could cause interference with the broadcast and cause problems. So these wires are specifically designed to minimize any creation of magnetic fields.